Today we're going to work on Unit 8, Lesson 1. A lot of what we're going to talk about you've already memorized in a different format. You just need to transition to understand what they're asking you to do. The first thing we're going to talk about are the fundamental identities. There are 6 of what we call the reciprocal identities. These are basic definitions. So the ones that you see highlighted are 4 identities that we're going to use all of the time in this unit. So just to clarify what an identity is in fact, if we talk up top and we say something like 1 plus 3 is equal to 2 plus 2, an identity tends to be an equation where when you simplify one side and you simplify the other, they come out to the exact same thing. In their original form, when I wrote the equation, they looked very different, but as an identity, they proof out to have the same value on both sides. Let's start with the highlighted in this box. By definition, the cosecant of x, if you remember, cosecant was related back to sine. Cosecant of x is going to be 1 over sine x. Secant of x related back to cosine, it's 1 over cosine x. Similarly, in the quotient identities, tangent x is sine x over cosine x. And cotangent x is cosine x over sine x. The 4 that I've written in red are going to be the ones that we use primarily. There are other definitions as well that we can talk about. Sine of x could be rewritten. Think about taking this, cross-multiplying and solving as 1 over cosecant x. Cosine could be written as 1 over secant x. Tangent is 1 over cotangent x, and cotangent is 1 over tangent x. The ones that I wrote in blue are formal definitions. You will see them in textbooks, but most of the problems we deal with, we're not going to need those. That we'll be able to use just the ones we've highlighted in order to get back to them without having to use a memorized identity. One big idea I do want to highlight is that we're going to talk today about sine squared x. When you see the squared next to the trig term, that should translate to you as sine x times sine x. Okay? If the squared was at the end, then that would mean that it would be the sine of x squared, all of which would be in the answer spot. Second big idea, we're going to devise the Pythagorean identities. So if I come over here, which I'm going to zoom in to look at, if this is a unit circle, so our unit circle comes around through here like this, we know that the hypotenuse is 1 of the triangle. We'll talk about 30 degrees, which is a unit circle value. We know at 30 degrees, the x and y values are root 3 over 2, comma 1/2. We learned through reference triangles that the x value is root 3 over 2 and the y value is 1/2. When we put those in the coordinate plane, that's where we generate these x and y values from. We also learned on the unit circle that if we want to talk about what is the cosine at 30 degrees, it's the x value. What is the sine at 30 degrees? It is the y value. So if we think about the triangle that we've drawn, root 3 squared plus 1/2 squared is equal to 1 squared. That's the Pythagorean theorem for this actual triangle. If we substitute root 3 over 2 as the x value, that is the cosine squared, 1/2 is the y, which is the sine, and 1 is 1, representing the hypotenuse, we generate our first important Pythagorean identity. It is always true that cosine squared plus sine squared is equal to 1. From there, we can do a little bit of algebra, which I'm going to slide over to show you. So notice I've written this exact identity twice. In the first one, I'm going to divide everybody by cosine squared x. And then I'm going to simplify. Anything over itself gives me 1. Sine over cosine goes back up here. Its alternate version is tangent. 1 over cosine, right here in red, up top. Let me go back for a second just to show you. Cosine squared, 1. Sine squared over cosine squared relates back up here to tangent. And 1 over cosine squared was right here with secant. Don't forget to make it squared because cosine was originally squared. This is my second Pythagorean identity. 1 plus tangent squared x is equal to secant squared x. And then we have this last area where we divide everybody by sine squared x. Cosine over sine relates back up to cotangent. Cosine over sine, but it's squared. So I'm going to get cotangent squared x plus 1 is equal to 1 over sine squared x, which is cosecant squared x. This is my third version of a Pythagorean identity. Typically, when students memorize these, I instruct them to learn the first, write it on the top of the paper, and then derive the other two. That's up to you. The other thing that's interesting is we talk about related letters. So up here we say like S goes to C and C goes to S. Cosecant and cotangent are in the same one. So actually you have a matching letter system if you're memorizing them. Now we're going to get to simplifying trig terms. So notice there's no equal sign. I'm not solving. I'm going to be simplifying these. Simplify. The easiest way to simplify is to convert things into sines and cosines. So I'm going to pull this out so you can see my thought process. Cotangent x is going to go back to cosine x over sine x times secant x, which is going to come back to 1 over cosine x. So using the identities up top, I'm going to substitute, and now I'm going to use my algebra skills and say, oh, two fractions multiply. I can cancel like terms top and bottom. That leaves me with 1 over sine x. Wait, 1 over sine x, I know what 1 over sine x is. It's the same thing as cosecant x. And I'm done. In example 2, I have a term out front. Notice I've switched up on you the variable. That is not a theta. I've got two terms on the inside. And to simplify, I'm going to take a distributive approach. So I have the sine times the cosecant, minus sine squared. If I look here in the front, I can convert cosecant to 1 over sine times sine minus sine squared. If we were in class, I would point to this and say to you, how many terms are here? 1 in the front, 1 in the back. This term, if I put it over 1, I can cancel top and bottom, just like I did in the last problem. That leaves me with 1 minus sine squared. Now, I'm going to put a star by this in red. Anytime in our notes the following happens, I'm going to use a red star. 1 minus sine squared. Wait a second. Sine squared, is that related to a Pythagorean identity? If I come back up here and I rearrange this, I get 1 minus sine squared x is equal to cosine squared x. Moving one term to the other side, it has the same value as the original equation, but now I can substitute 1 minus sine squared is the same thing as cosine squared. Be careful. You cannot use Pythagorean identities if you have squares. So, if this was 1 minus sine, I would have to stop. It is not a PI to substitute. Okay? That's not what we have. This is just like a little disclaimer I want you to put at the bottom of your notes. All right, moving on. Turning the page, 4 more examples. From this point forward, I'm going to refer back to the previous page, so please listen to what I'm saying verbally, and if you have questions, please see me in class. In example 3, I've got two quantities times each other. You've been taught the concept of FOIL, or double distributing. I'm going to take the first, which is going to be secant x, and I'm going to multiply it times the other two. When I do that, I get secant squared x plus secant x tangent x minus tangent x secant x minus tangent squared x. Okay, and you're going to say, well, how did that work out? Well, this came from the first two being multiplied. And then I can take this one and multiply it to get this and this. One second, please. I'm going to rip this out. Okay, so let's see it on the other side. Tangent x and secant x. This is a Pythagorean identity I probably want to keep in mind. 1 plus tangent squared, 1 plus tangent squared x is equal to secant squared x. In the middle, these two are the same thing. Okay? For the idea of plus sc minus ts. We know that the order of multiplication can change, so these are actually going to cancel. They are the same thing. Positive s times t minus t times s, we can reverse the order and we would cancel them. They're the same thing. So that's going to leave me with secant squared x minus tangent squared x. Anytime you have squares involved, check your Pythagorean identity. I can take this and I can turn it into secant squared x minus tangent squared x is equal to 1. This whole right side will substitute back to 1 as my final answer. Now, strategy-wise, it was evident we needed to multiply because we had two parentheses. In example 4, we don't have any parentheses, so our simplification is going to have to be through substitution, going to sines and cosines, or maybe we can use the opposite of distributing, which is greatest common factor. Two terms, both have secant squared. I'm going to take that out front. Leaves me with tangent squared x plus 1. Multiply back, I get what I started with. Multiply here, I get what I started with. We just showed in the last problem 1 plus tangent squared x was equal to secant squared x. So I can put that in here as a substitution. So this is my Pythagorean identity that I'm going to substitute. This was a Pythagorean identity that became 1. Bring down this secant squared x and multiply secant squared times secant squared is secant to the 4th x. And I'm done. Example 5. I'm going to rewrite this in a different order. Cosine to the 4th x minus 2 cosine squared x plus 1. 1, 2, 3 terms. What if instead of having 3 terms with cosines, I wrote it as c to the 4th minus 2c squared plus 1? I'm pretty sure you would know how to factor with that. You would tell me, oh, this would be kind of like binomial factoring. C squared minus 1 minus 1. The difference is, rather than just the letter c, I'm now going to have cosine squared. Cosine squared minus 1, wait a second, what is that? Well, cosine squared x plus sine squared x equals 1. Pythagorean identity. So each one of these, here and here, I think I'm going to be able to use a Pythagorean identity on. Cosine squared x minus 1 is equal to negative sine squared x. This becomes negative sine squared x. Negative sine squared x. Negative times a negative becomes positive sine to the fourth x. Final answer. In example 6, this is going to be an LCD problem. Okay, we're adding two fractions with different denominators. In the first fraction, I'm going to multiply by, take this first fraction, I'm going to multiply by 1 plus cosine x, top and bottom. In the second, I'm going to multiply by 1 minus cosine x. Distribute my 2 here and here. Distribute the 2 up top there. In the bottom, I'm going to FOIL. So I'm going to multiply these out. I end up with 1 minus cosine x plus cosine x minus cosine squared x. Cancels. 1 minus cosine squared x. These cancel, all of which is over below 4. So I've got 4 minus cosine squared x. I'm going to put a star here because we just proved up top here that 1, this could be rearranged. So if I come back up to here, couldn't I also write 1 minus cosine squared x is equal to sine squared x? Rearranging the first, moving the term to the other side. That's going to substitute and give me sine squared x. A couple options for seeing this. One of them is this. Notice how I split the fraction. If I multiply back, I get what I started with. 1 over sine, when we look back over here, is the same thing as cosecant x. So this becomes 4 times cosecant squared x. This problem right here is probably the trickiest part of everything that we've done. So you're going to want to review it before you start your homework.